All right, we're gonna get started on section 7.3, and the title of this section is Euler's theorem. That is a generalization of Fermat's little theorem. The objectives of this section are: first, we're going to define the concept of what is called reduced residue system mod N. And this concept we will need to give a self-contained proof of Euler's theorem. And then we're going to follow that by stating and proving Euler's theorem. We're going to prove actually a lemma before we do that. And then we're going to look at different applications of Euler's theorem. And one of these we will include actually the proof of the Chinese remainder theorem, a different proof using Euler's theorem. So let me start with defining the concept of a reduced residue system. Remember earlier we talked about what is called a complete residue system. On N, these are integers. And coming from, they are incongruent on N, and every integer is congruent to 1. And the least non-negative residue system mod N is 0, 1, 2, up to N minus 1. Now we're going to take a subset of this, which we call a reduced residue system. All right, so here's the definition. Again, let N be a positive integer, a reduced residue system mod N is a set of integers, positive, negative, cannot be 0, set of integers. Got a set of phi of, emphasize this, phi of n integers. Let's say R1, R2, up to R P to N that satisfy the following conditions. The first one, each one of these is relatively prime, the greatest common divisor of Ri, with n is equal to 1 for every I between 1 and R. Second, they are pairwise incongruent mod N. Means Ri is not congruent Rj for every I does not equal j between 1 and n. So such a set of integers called a reduced residue system, or sometimes we call it a complete reduced residue system because it contains the the largest number of integers that are relatively prime to n, and they are not congruent. The easiest way to give an example of a reduced residue system, you might start with a residue system, a complete residue system rather, a complete residue system mod N, and select the integers in this system that are relatively prime to n. Select the numbers in this system that are relatively prime to n. Or another way could be take different residue system and select one member of each, and so that it is relatively prime to n, and then select another one from a different residue system relatively prime to n, and it's not congruent to each other mod n and so on. So probably this is the simplest way to give just an example. Now let me give you an example of a reduced residue system mod 8, for example. So if I just want to give an example, I will start with a complete residue system mod 8 is this 0, 1, 2, 3, 4, 5, 6, 7. There are 8 members and none of this is congruent. So we call actually this is the least, okay, non-negative residue system mod 8. Now from these we're gonna scratch out the reduced that are not relatively prime to n. So we're going to keep the one that's relatively prime to 8. All right? So reduce the residue system. Mod 8. It's going to be, the 0 is going to be out 1, 2 no, 3, 4 no, 5, and 7. So it consists of, this one has, as you can see, T of 8, which is equal to 4. You could also take -3, -1, 1, and the 3. So this is another example of a, again, this is a reduced residue system. Residue system mod. Okay. There are infinitely many of them. Okay. Now we're going to start with the word stating and proving Euler's theorem. Remember that Euler's theorem is a generalization of Fermat's-Little theorem. We did start with a motivation in the previous section to determine whether we can replace, all right, the prime p for any composite number, and is it true that there is an exponent to which you raise a to for any integer that is relatively prime to n, assuming that the integer we are taking is n, is congruent to 1 mod n. And it turns out, yes, and that exponent is Euler's free function, all right? And so this is what we will be trying to prove. And to do this, we need the following technical lemma concerning reduced residue system. Right? In that R1, R2, up to Rp of n be a reduced residue system mod n such that Ri is actually smaller than or equal to n for every I. Here we're going to make this is bigger than or equal to 1. Right? So this is actually the least, in some sense, reduced residue system. Again, that is A, B, an integer. Actually, I want to make it positive integer such that greatest common divisor of A in M is equal to 1. Then we have 1, A R1, A R2. In other words, if I multiply each the elements of the residue system by A, this one is a reduced residue system. Reduced residue system mod n. 2, for every A R I, so every A R I is congruent to, we write it in words here. Is congruent to, well, let me actually say it in like this. AR1, AR2, ARC of n are congruent to R1, R2, up to RC of n in some form. In some form. Now there's a permutation that we apply to the indices of AR1, AR2, and so on. It will give you the same as R1 up to RC of n. All right. So the proof of this, first of all, in order to show that this one is a reduced residue system, we need to show that this AR sub I is congruent to n, and also these are not congruent among themselves. All right? This is the first part. So let's go ahead and do that. To show greatest common divisor, A I, and is equal to 1 for every I to phi of n. All right. I don't know in the theorem if I say there are I and J. No, that is in the definition. It should be phi of n. That's the number of those, not n. All right, so we're given, of course, that n is equal to 1, and by definition of reduced residue system, this one, each one of these n is also equal to 1. So we have the lemma back in, I think in this chapter 7. This implies that the product of these is equal. So this shows that, yeah, condition number 1 is satisfied. The second condition is to show that ARI is not congruent to ARJ mod n for every I does not equal j between 1 and phi of n. This should be phi of n if I wrote it actually. And here, well, we're going to assume by contradiction. So I'm going to assume that they are congruent. ARJ mod n. Now, since A is relatively prime to n, this implies we can divide by A, the congruence by A, both sides of the congruence, and this implies that I is congruent to R sub j mod n. And this in itself implies that n divides Ri minus Rj. And this implies that the absolute value, because I don't know which one is larger, unless we list it in an increasing order. So Ri minus Rj, in absolute value, this is going to be less than or equal to n. But we know that since Ri and Rj, they are between 1 and n, actually n minus 1, okay, so probably even n minus 1. Then the only way this the Ri minus Rj is going to be actually, let me see it here. It implies, yeah, this one is less than or equal to n minus 1 is, this implies the Ri minus Rj absolute value must equal to 0. And this implies the Ri is actually equal to Rj. But this is a contradiction because we are assuming I does not equal to j. And those integers are not even congruent to each other mod n. All right. So this takes care of the second condition. So therefore, we have those integers, multiples of A, form a reduced residue system. Write this down. So therefore, yes, A1, A2, A3, and is a reduced residue mod. Next, we want to show that given an A on I, and we need to find there exists a unique R sub j such that A Ri is congruent to A R sub j mod. So in other words, they are congruent to each other in some order. So ARI, there's an RJ that is congruent. And to do this, we're going to apply the division algorithm. To ARI and N. Okay? Which means I'm going to be writing ARI is equal to Q sub I N plus S sub I. And I'll use R for remainder here. All right. Where QI and S sub I exactly less than n. All right. Moreover, we have the ARI also have the ARI is congruent to SI with the same remainder when this one is congruent to the remainder in here, mod n. And this is a proof for every R. And the n. Now we also have the SIs are between 1 and n. And now we're going to see that they are relatively prime to n, so they must be congruent to one of the RIs. Now let's see that. Okay, so we have the greatest common divisor of SI and n is the same as the greatest common divisor of ARI and n. Because these are congruent to each other, then they're going to have the same greatest common divisor. And now this one, we know it is equal to 1. So it means that the greatest common divisor of SI and n is equal to 1. Now this implies since SI is between 1 and n, and of course the greatest common divisor of SI n equal to 1, then SI equal to R sub j for some j. And this is between 1 and 0. And this is it. So now together with this congruence in here, and this implies ARI is congruent to SI, congruent to RJ mod n. Yeah, this will take care. Now we go ahead and state Euler's theorem and go through the proof. All right, Euler's theorem simply states that Fermat's theorem, in some sense, okay, holds for every composite number. So this is theorem 7.5. Euler. Again, with n bigger than 1 be a positive integer, and a in Z relatively prime to n. Then a to the p of n is congruent to 1 mod n. All right. Before we give a formal proof for Euler's theorem, I'm going to consider an example that will illustrate the idea in the proof. Okay, so you're going to see it, in other words, and then we go ahead and implement this idea for the general proof of Euler's theorem. So here's an example. Let's take n equal 8 and a equal to 3. Of course, in here we have 3 and a are relatively common. Now we're going to start with consider a reduced residue system. A reduced residue system mod A. Could be anyone, but I'm going to actually take this, which is 1, 3, 5, and 7. Then I'm going to multiply each element of this by 3. I'm going to multiply each element in the set by 3. So what do we get? We get, of course, a new 3. I'm going to put it 3 times 1. I'm just going to leave it like this. 3 times 3, 3 times 5, and 3 times 7. And this is also, this one is a reduced residue system. A reduced residue system. All right? Mod A. Moreover, we know that this new residue system, those numbers are congruent to the original one in some order. And I want to write that down. So we have 3 times 1, all right, and comma, the 3 times the 3, 3 times 5, 3 times 7. This is congruent to the first one is a 3, the second one 9, mod 8 is 1, and this is 15, mod 8 is 7, and this is a 21, mod 8 is 5. So the same, except in just a different order. Now, this means that when I multiply, so I'm going to multiply all right, the 3, that the elements or the integers on the left side. Of the above equation, of the equation above. And what do we get? We get 3 times 1, 3 times 3, 3 times 5, 3 times 7. And this is equal to, there is a 3 appears 4 times, and this 4 times is actually phi of 8. And then we have, of course, this is multiplied by 1, 3, 5, 7. All right? But we have so we have this, and now since these are congruent to mod 8, so we can say this is actually is congruent to one other thing in here. One other thing. I have also one more thing. Is the greatest common divisor of 1 times 3 times 5 times 7 and 8. These are relatively prime. This is equal to 1. All right? And then we can divide both sides. All right? Or let me actually write this as a congruence. Okay, equality is actually stronger. So I'm going to put in here mod 8. I'm going to write it as a congruence. So then we can divide both sides. Let me actually say this. This is congruent to 1 times 3 times 5 7. I want this mod 8. Because this product is congruent to this, and this product is just equal to this. So this is congruent mod 8. Now we're going to divide by, since the greatest common divisor of the product of these and 8 is equal to 1, then we can divide by both sides of this congruence in here. We put the start by 1 times 3 times 5 times 7. And what we get on this side a 3 to the field of 8. And this side, all these integers cancel out. We end up with 1 mod 8. And this is exactly what Euler's theorem is stating. So the main idea, in this proof is to take a reduced residue system, then multiply by that A that we are considering in the theorem, and then just do this trick. All right, so let's go ahead and present the general proof. And this proof does not use any of the properties, earlier properties of the V function, that it is multiplicative, and the way we evaluate it, and so on. We're going to present another proof using these properties. So we call this is a self-contained proof. It doesn't use anything except this concept of reduced residue system. All right, so we're going to let R1, R2, up to R, U, N be a reduced residue system mod N. Doesn't have to be the 1, 3, 2, whatever we took in there. Residue system mod N. We're going to multiply each one of these elements by A, then we know by the lemma that this AR1, AR2, ARUN is a reduced residue system mod N, and its elements are congruent to R1 up to R3 and in some order. Now we're going to take the multiply these. We're going to consider the product. Let me see if I want to do it actually using the But before I do this, let me, so that I can actually minimize the writing in here. So what we have is, which we have from here, so we have A, R, I is congruent to R, J, all right? For every I and J between let me see how I want to say this one. Let me write here. To be a little more precise than what I had in here. This is important to say that for every A R I, there exists an R J, there exists a unique R J such that A R I is actually congruent to R sub J mod. Then we're going to take the product of all of these, all right? And the product is going to be over I, and we're going to take the product of these over J. So we take the product, I equal 1 to phi of n, A R I. We could multiply each one with the corresponding one, so at the very end, we can collect the T of n R sub j mod n. Now, the effective product, the product on the left, means for every I, we're going to take AR1 times AR2 and so on. And then I can split it into two products. The one for the A's, from here, we can say this one is the product I equal 1 to phi of n A, and the product of I. All right, let's take all the 8 out and multiply them, and this is congruent to J equal 1 to phi of n R. This product is like adding up a constant. You get the multiple of that constant, and here you get the A to the phi of n. And then this. Now, I could use a different index on this. All right, because this is running through all the integers from 1 to phi of n and phi of j, so it is the same as I equal 1 to phi of n r sub I. You can rename them. And then since we have the greatest common divisor of Ri and n is equal to 1 for every I, this implies a product of these with n also is equal to 1. And finally, we can divide like we did in the example. So we divide both sides of star, because this equation star, by this product. This one is phi of n. All right, I equal 1 to phi of n r sub I, and we obtain A to the phi of n, because this product that we cancel out is congruent. In here we end up with 1 mod. And this completes the proof. Okay? Very simple, nice proof, no extra properties we see. Now, we can now prove Fermat's theorem as a corollary to this. And this is actually the advantage of this proof. It does not use the second proof. We're going to be using actually Fermat theorem as part of the proof, but this one it doesn't. So we can say that it follows as a corollary. All right, corollary. This is Fermat's theorem. Yeah, let P be a prime and A in Z relatively prime. To B, then A to the P minus 1 is congruent to 1 mod. The proof by Euler's theorem we have A to the field P is congruent to 1 mod P. That's what Euler's theorem is saying for any integer that is relatively prime to P in this case. But we have P of P is equal to P minus 1, so this implies A P minus 1 is congruent to 1 mod. Very simple, nice proof that follows from Euler's. All right. Our next objective is to give examples of applications of Euler's theorem. There are going to be several examples that we're going to be considering. First one is to actually use it to reduce numbers or powers of integers mod a certain integer. And in particular, we're going to look at this example. So here are some applications. Of Euler's theorem. So here's the first one. One, reduce large powers of an integer n or integer a mod n. So, look at an example of this. Say that we wanted to find the last two digits of this number, 3 to the power 256. Or we can remodify this and say find the last digit or the last 3 digits and 4 digits and so on. Actually, you can find as many digits as you like, all right? And the idea is this. So we're going to consider this number mod 100. Consider 256 mod 100. And we're going to see how wide is going to tell us the last 2 digits. If I want the first digit, is mod 10. If I want 3 digits, mod 1000, and so on. All right? Idea is this. First of all, let's look at 100, which we calculated this before. There are 2 primes, so 100, and the primes involved in this is 1 and 5. and then we have this is 4. So we have a 3 to the 40, and of course the 3 is relatively prime to 100, so this one is going to give me a congruent to 1, mod 100. Then we're going to apply the division algorithm to 40 and 256 to write that as okay, by the division algorithm. We have 256 is equal 40 multiplied by 6 plus 60. And this implies that if we want to look at the 3, 256, this is the same as 3, 40 multiplied by 6 plus 16. And this is equal to 3 to 40 to the 6 multiplied by 3 to the 16. Now we're going to do congruent to mod 100. The 3 to the power 40, this is congruent to 1. And this is, we raise it to the 6th exponent, and this is 3 to the 16. So at the very end, we come up with this is 3 to the 16 mod 100. Still, this is very big number. So we can use the successive squaring to calculate what 3 to the 16 equal to. So we start with 3 squared. This is, of course, equal 9, so it's congruent to 9 mod 100. And we're going to take the square of this. So this becomes to the 4th. And this is 81. Still we are under 100. Then we take the square of this becomes a 3 to the 8th. And 81 is squared. Now we need to reduce this mod 100. All right, and it reduces to 61 mod 100. And then we take the square of this, will be 3 to the 16. And this is 61 squared, reduce mod 100, you come up with the 21. Mod 100. All right, so in other words, this is what we conclude. That 3 to the power of 256. This is congruent to 21 mod 100. And this implies that 100 is going to be divisible by 3 to 256 minus the 21. And this implies 3 to the exponent 256 minus the 21 is going to be 110, where k is an integer. Now, when you take this to the other side, is equal 100k plus the 21. Now, all the numbers that we're going to be multiplying by 100 in here, all right, they're going to have their first 2 digits going to be 2 zeros, right? And which means that when you add it to 21, so this is the last 2 digits. And the 3 to 156. So the last 2 digits is 21, all right? And you can see how we could generalize this is to 1 digit, 3, 4, 5, and so on. All right. The next application of Euler's theorem is to provide us with what is called multiplicative inverse, all right, or an integer mod n. All right. Let me define this concept first. So again, the second application is use Euler's theorem to find a multiplicative inverse mod n. Here is the definition. Again, let n bigger than 1 be an integer. And we're going to let and a in Z, an integer a prime is called a multiplicative inverse of a mod n if the product of a prime times a is congruent to 1 mod n. In a sense, similar to the actually ordinary definition of a multiplicative inverse of a number. It is the number when you multiply by the other number, you come up with 1. Only thing here, we replace this by a congruence relation instead of equality relation. Now, the first thing we want to notice that in order for an integer a to have a multiplicative inverse, it must be actually relatively prime to n. And this is an f and only. So we have this remark. An integer a has an inverse mod n if and only if. This is a theorem, but it's not very big of a deal. So we're going to the remark. All right, if and only if a is relatively prime to n. All right, let's apply it and to prove this. So let's assume that a is relatively prime. Is the proof. Let's assume that a is relatively prime to n. Let's consider this equation. Ax congruent to 1 mod n. So this is a linear congruence relation. Since we have greatest common divisor of a and n is equal to 1, and 1 divides the right-hand side of the congruence, which is 1. This implies that linear congruence equation has a unique solution. we satisfy this equation, square root to 1 mod n, and this implies A has an inverse. A has A prime as inverse mod. Sometimes we use the word, instead of saying multiplicative inverse, whenever the the context which we are talking about, then we don't need to mention multiplicative. The other way around is as simple as this. So let's assume that yes, there is. Okay, going this way. Let's assume that A has a multiplicative inverse mod, let's say again A. And the multiplicative inverse, by the way, it's unique, of course. That is the case as we see from the first part. So this means this implies that we have A prime is equivalent to 1 mod n. And then I want to show that actually A is relatively prime to n. All right? So let's assume that greatest common divisor of A and n is equal to B. All right? Now, what we have the linear congruence AX congruent to 1 mod n has a solution, namely because A prime it does actually satisfy this by the necessary and sufficient condition for linear congruence equation to have a solution. This D, which is the greatest common divisor of A and n, must divide the right-hand side of the equation. All right? This is back in chapter 2. Okay? Actually, let's select since the linear congruent has a solution. This implies that D, right, the greatest common divisor must divide 1. This is the right-hand side of the congruence equation. Well, what does this imply? Imply that actually D must be equal to 1. The only number that divides 1, positive number, and D is positive, this one. And we're all right. Now, let's see how actually Euler's theorem, that is our concern, actually does give us a multiplicative inverse of a given integer. All right? We put this as a remark, and here again, let n bigger than 1 and A in Z such that A equal. By Euler's theorem, we have this A to the P of n. This is equivalent to 1 mod n. We also know that phi of n bigger than or equal to 1, all right? Which means that phi of n minus 1 is bigger than or equal to 0. Let's take this, a phi to the n. I can write this as a multiplied by a phi to the n minus 1. Now the exponent, the new exponent on the a here, is this is bigger than or equal to 0. So in other words, it's not a negative exponent. So this makes sense, means the worst it can be is this is equal to 1 if this exponent is equal to 0. So this statement is true. And I know this one is congruent to 1 mod n. That's Euler's theorem. What does this mean? This means that a to the phi minus 1 minus 1 is a multiplicative, is the multiplicative inverse of that. In fact, remember that we said that phi of n is always even as far as n is bigger than 2. So we're going to see that for 1, the multiplicative inverse itself, and for 2, all right, the multiplicative inverse, it's going to be mod 2. I'm saying it depends on what it is. But, so it's going to be either 1 or 2. Or 1, actually, 1, to take multiplicative inverse of 2. All right, so this is it. So let's look at an example. So this makes it easy because we have an effective method of finding the value of Euler's function for different integers. Simple. So let's say we're going to find the multiplicative inverse let's find the multiplicative inverse of a equal to mod 9. All right, so all we need is we need phi of 9. Integers between 1 and 9 relatively prime to 9, and there are how many of these? 6. Okay, or you could use, of course, the formula for what is phi of 9. So now we know that a to the 6 is congruent to 1 mod 9, and then this one is actually 2. I want to use 2 here. It's true for any a relatively prime. And then we write this one as 2 to the 5, which is phi of 9 minus 1, okay, congruent to 1, 9. And which makes this is the multiplicative inverse. But this one is congruent to 32 mod 9. This is actually is congruent to 5 mod 9. So this implies 5 is the multiplicative inverse of 2 mod 9. Now, by the way, the 5 that appears as an exponent and this 5, it's an accidental, they are equal, not always the same. All right, it happens that this is 32 congruent to 5 mod 9. If you subtract, you get 27. All right. Another application is to solve linear congruence equations. We can use and actually this is based on this idea of inverses. And this method of solving linear congruence equation is the closest it comes to solving regular linear equations in one variable. Okay, so this is application number 3, I think. Okay, use Euler's theorem to to solve linear congruence equations in one variable. All right, now remember a linear congruence equation is an equation like this. And we also know that this has solution if and only if D, which is the greatest common divisor of A and divides B. And if this is the case, there are D incongruent solutions mod n. It's two different ones. And the idea, if we know how to find one, then we can find all the others from this one. Okay, this is a procedure that we have covered in chapter 2. All right. So first, I want to consider the special case. All right, a special case where the A and N are relatively prime. Okay, so special case. Where D, which is greatest common divisor, A and equal 1. So this means that this implies that the congruence equation has a unique solution. Now, remember that if I have this is just a regular equation, algebraic equation AX equal 1, that to solve this one, we multiply by the B, sorry, even B, okay? The solution of this is to divide out by B. Okay, and of course, if B is divisible by A, then the solution is going to be an integer. And really, dividing by B means multiplying by the multiplicative entity. And this is as an equation, of course, as a congruence in here, that's what we're going to do. Now, since we have A and N is actually, these are relatively prime, so this implies that A has a multiplicative inverse mod n and given by A to the phi of n minus 1. That's what Euler's theorem is telling us. So if I multiply both sides of this equation by this, so if I multiply both sides, AX equal A P n minus 1P mod n. The left side is going to give me 1, okay, because it's going to be A to the phi of n by Euler's theorem, and then we get a solution. So this implies X equal this number, P of n minus 1 multiplied by B is the solution. All right. Well, let's look at an example. And we're going to use small numbers so that we don't have to use a calculator. And then we will look at the general case. Here we can obtain it from the actually the special case. So here's the example. Let's look at the 3x congruent to 7. Mod 10. Again, the idea is not really just solving here, just to illustrate the method. Okay? This is very, very simple congruence. All right, so we need phi of n is equal to 4, and the solution x. Remember, it's going to be the 3 to the third, which is 4 minus 1, multiplied by 7. All right, and we're going to, of course, reduce this mod 10. When you do the calculation in here, come up with this is a 27 multiplied by 7, and this is congruent to the 27 is congruent to actually 7 times 7 mod 10, and 7 times multiplied by 7 is congruent to 49, and mine, let me see it here. Yeah, so this one is 4. 49 is not odd. Yeah. I don't know why I have 7 in my notes here. Let me double check in here. So 9 times 27. All right, mod 7. 7. Yeah, so this is 7. All right. Now, let's look at the general case where we don't have that A and N are relatively prime. So this is the general linear congruence equation. X congruent to B mod, where D is greatest common divisor of A and could be bigger than or equal to 1. And we're going to assume that this has a solution. D divides B. And what we need, we say we need one solution. And what we could do, we could divide both sides of this congruence equation by D. And we come up with a new congruence equation. And we need to divide the n also by D. So if I call A over D to be A prime X, B prime mod N prime. So this congruence relation, we have the greatest common divisor of A prime and N prime is equal to 1, and this is the special case. Now, once we solve this, then we can actually find a solutions mod N by multiplying the solution by D. Okay, so in other words, we go back to the original equation. And then we can generate all the other solutions. All right. Next, we're going to give another proof of Euler's theorem. And then we'll actually do the, let me do the Chinese remainder theorem first, all right, and among the applications, and then we give a second proof. All right, here is the, remember the Chinese remainder theorem, it deals with a system, or a special system actually, of linear congruence equations, and it says that the system has a common solution. All right, so here it is. Okay, so this is number 4, and this is use Euler's theorem to prove the Chinese remainder theorem. All right. the Chinese remainder theorem, we have this. We have a system of linear congruences of this form, right? X is congruent to A1 mod N1, X congruent to A2 mod N2, and so on. And X is congruent to A sub R mod N sub R. Where these n's are relatively prime, and I and j equal 1 for every I does not equal j. And these are integers, positive, negative, whatever they are. All right? So the Chinese remainder theorem says that we need to show that the system has a solution, also a common solution, mod the product of all the integers. All right? Since these are relatively prime, they're supposed to be congruent to the least common multiple of these, but it is the same as the prime. All right. The idea is this: we need to introduce some notations to work with this. First, we're going to take the product of all the n, 1 up to n sub r to be n. And we're going to also define another set of integers. So here's the proof. We're going to let n equal n1, n2, and r. And we're going to define with n sub I equal n divided by the n sub I. Okay, and this is for I equal 1, 2, up to r. So in other words, this n sub I, okay, so remember that n sub I is equal to n1, n2. And I remember we put the hat on this, means we are covering that, it's not along this product, and then up to n sub I. Okay, we're going to be having this or remembering this. All right, now then from this, for any j does not equal to I, and these are between 1 and r, the n sub I is going to divide n sub j, all right? Because the n sub j in here, the n sub j is missing, but as far as this is not n sub j, this little n, then it would divide, because it could include all of this. And this is true, of course, for every again, when less than or equal, I does not equal j, less than or equal. This in itself implies this relation that n sub j is congruent to 0 mod n sub I. And again, this is true for every I does not equal to j between 1 and r. All right. Now I claim that the following is this common solution, okay? And really the idea comes from using the Euler theorem to solve linear equations, linear congruence equations, not like what we did before. We just want to combine these solutions together. So here is the claim that x equal a1 n1 phi of n1 plus a2 n2 phi n2 and so on up to a sub r n sub r phi of n sub r is a common solution to each equation in the system mod n, where n is the product. Now let's prove this claim. So this is x I want to show, this one. Now if you take each one of these, all right, this one, each one of these is congruent to 0 mod n1, okay? Remember that we have since n sub j is congruent to 0 mod n sub I, for every I does not equal to j, this implies that A1 for x equal to actually A1 N1 P of N1 is congruent to A1 mod N1. Because all others, since A, J, Nj, Phi of Nj, this is congruent to A sub j multiplied by 0 mod N1. All others, okay, for j does not equal to, here j does not equal to 1. As far as doesn't equal to 1, all of these are going to be congruent to 0. So for the only term left from here, it actually satisfies the first one. And similarly for anyone, okay, so x, which is equal a2, n2, phi of n2 is congruent to a2 mod n2. But, and so on, so x is equal to, one thing actually I have to, let me take this A1 off this step. Let me just put this one, x actually is congruent to this, or this, and so on, okay? So we need now to use Euler's theorem. This is our phi of n sub r. But we have the one other thing. Since N1, let's go with N1. So this is equal N2, N3 up to NR is relatively prime. To n sub 1, little n sub 1, means the greatest common divisor is equal to 1. This implies by Euler's theorem that n1 p to the little n1 is congruent to 1 mod n1. Similarly, for the second one, A2, and so on. So from here, then we can conclude that we have these congruences. So this becomes congruent to A1 mod N1. It means that the X, all right, is going to be congruent to A1. Because all other elements in the X are, mod N1 are congruent to 0. And the same thing in here, A2, mod N2, and so on to the last one, which is A sub R, mod, and so on. So the same X is congruent to all of these, then this would imply by a property that we proved earlier that X actually is a solution to the congruences mod their part, mod, and this is actually the Chinese remainder theorem. All right, one thing left which I want to finish up with, and this is a second proof of Euler's theorem. And again, this proof does depend on properties of Euler's free function, and also it uses Fermat's theorem, because we're going to do it by looking at that special sort of cases. All right, so this is second proof. Of Euler's theorem. First of all, we're going to prove it for it for R zero prime. So we're going to let P here prime and K is bigger than 0, it's a positive integer. All right, and A is an integer relatively prime to P to the K. All right, to show A to the P to the P to the K is congruent to 1 mod P to the K. Now we're going to do this one by induction on K. For the base case, for K equal 1, we have A P to the P to the 1 becomes A P minus 1, and this is congruent to 1 mod P. This is by Fermat's theorem. All right, so we cannot use that, if we only have this proof, we cannot then conclude that Fermat's theorem is actually a special case, or or a corollary. We cannot prove it as a corollary. It will be a special case as far, but not as a proof. All right, now let's set the inductive hypothesis. So we're going to assume that statement is true. And the statement holds for some k bigger than or equal to. All right, I don't have to write the statement, means just this theorem is true for not all of k, just some k. All right? And then I want to consider the theorem for phi to the power pk plus 1. All right? And to do this, so we need to look at phi of pk plus 1. Now we could write that down. So we're going to consider phi of pk plus 1. This is equal to phi of p times. Actually, let me write it like this, using the other formula. So this is p k plus 1 minus p. And then I want to factor out a p out of this. Now, this second factor in here is actually phi of p to the k. So this one is p times p to the k. All right, now let's take a to the phi of p to the k plus 1. So this is equal to, I want to replace this by p to the phi of p to the k. All right? Now, by induction hypothesis, and this one is again equal to a p to the k, like this, and we could put p outside. Now, by the induction hypothesis, we have a to the phi to the p to the k. This is congruent to 1 mod p to the k. All right? And this itself implies that p to the k divides, of course, a to the p to the p to the k minus 1. And which also implies that a to the phi of p to the k minus 1 is a multiple, the q times p to the k for some integer q. Then we can, one other thing in here, let me go up. So from this equation, we can say that e to the power e to the k is equal 1 plus q p to the k. All right? So we take the one to the other side. Now let's go back to this a phi to the pk plus 1. Remember that we wrote this one as a to the phi to the p to the k, all of this to the p. Now I'm going to replace the inside the parentheses by 1 plus q p to the k to the p. Now I can use the binomial theorem. Okay? So we're going to use the binomial theorem to expand. Now I'm going to use the binomial theorem. So this is equal to 1, actually pp or p0. Then we have p1 q p to the k plus p2 q p to the k squared and so on. And the last term is going to be pp. Which is going to equal 1, but I will write this, and the q p to the k to the p. Like that. All right. Now let's see what this is equal to. So this one is 1. P1 is equal p. So q p to the k. And this one, it's going to leave it, the binomial coefficient. This one I'm going to split it into actually q p. Let me see how I want to write this. I'm going to put a square in here. We put a square on the q. And this one is supposed to be b to the power of 2k. And I want to write it as k plus 1. All right, and the remaining part of the 2k is going to be k minus 1, like this. So when you add this up, you come up with 2 to the k. And I'm going to do this one for every term. And this one is going to become, this is equal 1, q to the p. And this one is going to be p to the power qp. Okay, and I can again write that one as p to the power k plus 1 multiplied by p to the power p minus 1 k minus 1. Okay, so when you add this up, come up with p to the power k. Now, each one of these, this one is going to be congruent to 0 mod p to the k plus 1. And everything else, because it contains that, so this is 0 mod p to the k plus 1. So all cancel out, and then we end up with, and also this has a p to the k plus 1, so also this is congruent to 0 mod p to the k plus 1. So the net result is, we have the a to the p k plus 1 is congruent to 1, which is this one mod p to the k plus 1. So in other words, the theorem, yes, it's true for k plus 1, whenever it's true for p to the k, p to the k. And by induction hypothesis, so this statement is actually true. All right, so let's see what we have here. So we have the theorem is true for every power of a prime, for every prime, for any prime. P was arbitrary. So this means that we have for any E and K bigger than 0, A to the P, P to the K is congruent to 1 mod P to the K. Now let's take an arbitrary integer n. And let's assume this is of course P1, K1, P2, K2, PR, KR. So this is be the prime factorization. Of n. Now we're going to take A to the n. Of course, A is relatively prime to n. So this one is going to be A to this product. We need to take phi of n. Sorry, phi of n, which is phi of this. But since phi is multiplicative, and of course these are relatively prime, these prime, so this is equal to A, the product of phi of p sub I, k sub I, I equal 1. All right. Now one other thing. Let's look at this phi sub n, which is equal to phi for this product. Actually, let's just write it as this product. Phi sub I, k sub I equal 1. This implies that phi of pi ki divides phi of n for every I between 1 and 1. So what does this mean? This implies that the phi of n over phi of pi ki, this one is an integer. Now I'm going to take the one other thing in here, keep myself organized. So let's actually have this. There's one statement probably I don't need it here, but that's fine. So let me take the phi. We have this, is it true, right? Pi k sub I. We know this one is congruent to 1 mod pi k sub I. This is true for every I from 1 to R. Now, when I raise both sides, okay, so we're going to raise or take the raise, piercing raise both sides of the congruence to this exponent, to the exponent phi of n divided by phi of pi to the ki. So we're going to raise this to this exponent, and this leads to, in other words, there's one statement I wrote before, I got this last line in here, we don't need this. So this side becomes a to the phi of pi k sub I. Now we're going to raise this all to the phi of n divided by phi of pi ki. And this is congruent to 1 to that exponent. Of course, we're not going to change anything, but let me write it. Mod p sub I, k sub I. Now, of course, these cancel out, and we end up with a to the phi of n is congruent to 1 mod, this is first one, mod bi ki. Now, the last step, since each one of these is congruent to this is for every I, like we did with the Chinese remainder theorem, this implies it is congruent to their product, okay, to all the product to this. So this implies this is congruent to 1 mod the product of all the primes. And of course, this is equal to that. All right, this is it. And you can see the previous proof is more elegant, nice, straightforward. Doesn't use any of the properties of phi or anything like this. All right, but at least you do have the two proofs now. All right, let's stop right here. And this actually, no, there's one more section in chapter 7. I need